Hello there, today we'll be doing word break. Alright, so in this problem, what we're seeing here is a word called a string, and we're trying to find out if we can use these items in the dictionary to create that word. So Leetcode can be created because we have the word leet and code. Here we have apple and pen, so we can create the word apple, pen, apple. And for this one, we create cats and dog. Cats and dog. We have cats. We have dog. We have sand, but don't have. We have cats. So we don't have it. We cannot fulfill that condition and get the item. We can have OG, and that would fulfill it. If we had cats and cats and OG. We have sand and cat, and we have dog. And if we had an cats and dog, then we could also produce this true. However, we cannot. Let's see the constraints. So the constraints of our length of a string is 300 characters. The length of the dictionary is 1,000. So, and the word is 20. So one thing we know for sure is that this particular word is going to be only 20 characters long. And so because that is 20 characters long, it is much easier to match 20 characters rather than match 300, all the strings. So let's match that by indices. S and word dict are only lowercase integers, and all strings of word dict are unique. Okay, very good. So let's think about apple and pen first. So let's do this brute force. So we can choose apple and pen for apple, and so for this word, apple, pen, apple. Let's choose. So let's eliminate this particular word, and so that we can find out what we need to do for these words here. So by eliminating, we can, process of elimination, we can only select 5 characters, let's say apple, to for this. It is impossible with pen, so we have to put an X there. So with that, we have separated out this word. We only need to figure out apple pen now. So, let me put that back together and just grab this section here. So we're going through logic with the words. So we can choose apple, pen again. Those are our only options. So we can check if the next 3 characters are going to be pen or apple. And if we can fulfill that condition. And it looks like apple is an X, and we have to go with pen. So what we have now is we're left with apple. And now we'll do one more time. And what we have here is apple or pen, and that means that we can either choose apple or pen, and apple fits the bill, so we choose apple, and pen is X'd out. So that is our decision tree. Our decision tree is to look at the word at each index and see if we have any words that fulfill that. Once we've completed that, that means we can eliminate that part of the word from now on. And with that, we have a smaller problem that we need to solve. And that's how we're going to use dynamic programming, because everything before this can be true. Like, we found a way to get this word. And if it's true, then if we can get to this particular area, and that's true, then the whole thing is true. So how we're going to do this is we're going to do this top down first. And then we're going to do this bottom up. So to do this top down, let's set up our table. So we're going to have a DP to represent every character that can be false or true. So length of S plus 1. Then we're going to set the length of S, the last character, that is past the last character, to be true. With that, once we get to that last character, that means that we must be returning true. So we're going to run a DFS of I, and if of course, if dp of I exists, then we can return, because we don't need to do anything more. That means that's true. We don't want to mess with it, and that's good enough for us. So DFS of I plus 1. This will bring us all the way down to a single item. And so now with that, we can run our for loop. I wonder what will happen when I read this code later. So anyways, so word dict, for every word, what we're going to do is if I plus length of word is less than or equal to length of s, and word equals s I plus length of a word. So basically, this one, make sure it's less than the length of the string, and this one, make sure that this word is equal to the word in the string. So now, we're going to set dp of I equals, if that's true, we can go up to that particular location and figure out if that's true. So you will see shortly. So now with that, we can check if dp of I, that means we don't need to do any more work. Let us drop, we found the item for this particular location, and let's stop, let's return. So we do dfs of 0, so that's our 0 index of our apple, pen, apple, and we're going to return whether at that particular index it can be created with the words inside the dictionary. So let's run the code. Let's a little error here. So whoops, let's set a test case called apple, and let's set the items to be apple and pen. So let's run the code. Let's print out that dp every time we have to access the DFS call. This shouldn't be too long. Let's print it out. As you can see here, this is our first character. This is past the index, and as you can see, we dig deep. Oh, okay. Well, we don't have enough output to show that. And also my face is in the way. Let me just get that out of the way. Sorry. Whoops, wrong one. Okay. So we need to let's print a change whenever this is true. How's that? Oh, yo. Okay. Yeah. It's not working. So how about here? I'm just not having any luck here. This is just, yeah. So as you can see here, true, and we've lost apple, and then we have pen here, and then we have another apple, and that's how we got our DP. Yeah. So what we want to do now is to do this bottom-up approach. And this requires us to read from our top-down approach and grab it. So dp equals false times length of s plus 1. dp of length of s is equal to true. So then let's set the for I in range length s minus 1, so that's our last index, minus 1 and minus 1, and that way we can grab each item. So yeah, okay, so if dp I break, same thing, so for word in word picked if I plus length of word is less than or equal to length of string, and word is equal to the s of I plus length w. That's it, and we set the dp of I equal to the dp of I plus length of word, because we're taking that entire word from this particular location, and we're looking if that particular location we can fill in this section, but was it filled in before? And if it was, we can break, because we filled it in. We're done. And with that, we return dp of 0. And it looks like we're returning true, and we're good. So yeah, that's how we do it. Let's see if there's anything we could do better. Maybe we don't need that. Do we need that? Not sure. Run the code. And also, why are we let's submit. Why are we printing stuff? Is that actually happening? Anyways, yeah, so that's how we do this particular problem. It looks like its bottom up is slower than top down for some reason. But that's the translation. It's basically going, we did a DFS call, we went all the way down. Let me show you. And then we're going all the way back up. So to show this, I can show you what's happening here in words. So print the word that we're looking for and the item that we're getting. Okay, so let's run the code. Oh, what happened? Something's wrong. Oh, we missed a quotation mark. Okay, so we see that we grabbed the first, see this is the first item, LE and pen. And then we tried to grab the next 2, next 3, next 4 items, and then we found the 5. We found that item, and we're done. Then we're moving on to the next item with the N and NAP, and then ENAP, and then it looks like we haven't found anything yet, and then we eventually found a pen. And after that, we move on and onward until we found Apple. And that's how we solve this particular problem. What did we learn, and how am I supposed to solve this during my interview? Like, how am I supposed to find out about this word break? About, yeah, I can see how I can do it. Like I can grab this letter, check it, and then check the entire dictionary, and then for this word, and then go for an entire dictionary and check this word, and that would take a really long time. Like, there's no way to do that, because we check this first word and we have to check the second word, and so on and so forth. It's like it's a decision tree. And so what did we just say? Decision tree. And so with a decision tree, we can save our I guess code, and by working at each item, we can make that decision tree much more simple, like, because we're looking for each item rather than all the items. And so I think that is the way to solve this during a coding interview. It is to look for this pattern of, oh look, we're doing repeated problems. We're looking at this code multiple times for different words. We're looking at apple. For apple, we're looking for this word for apple, this word for apple. We're looking at every section for apple. And the repeated work can be saved if it was true. So anyways, I think that wraps up this particular problem. I hope you enjoyed the video. I don't know if the lesson here was clear enough, but the lesson is to see repeated work and minimize repeated work. And there we go. That's it. Hopefully you've figured this out as well. I don't know how much better I can explain this. But let's think about the O of n time. So we have to go through the entire string once, as you can see here. So that's n, and then we have to go through each word. So let's say that's m. So n times m, and then we have to do matching for this word. So m times m times the size of the word, m and l. Yeah. It could be n as well, because it could be the full length of the word. That could be true too. So n times m times n. And what's the size? Well, the size is going to be length of the string, which is 300, constant. So that's all. Hopefully, I think I brought out as much as I could for this problem. I think with more problems, we could bring out more. I think there is still more to learn from this problem. There's always more to learn everywhere. But this video is getting pretty long. It's 17 minutes now, and I thank you very much for watching. If you enjoyed the video, like and subscribe. If you want more, check the link in the description below. Thank you very much, and have a good one.